and mathematical tools. Statistical analysis can be divided into three groups. Number one is the univariate statistical analysis, test hypothesis involving one variable. Number two is the bivariate statistical analysis, the test hypothesis involving two variables. And number three is the multivariate statistical analysis. And it involves a set of variables or multiple variables. I'm sure you know and experience the world is a complex place. Also, most businesses' problems are ill-defined. As researchers become increasingly aware of the complex nature of these business problems, they gain a greater appreciation for more sophisticated approaches to data analysis.
As humans, we long to relive the past. This yearning to hold onto the past is a common psychological experience. The psychology of consumption is of interest to many people who are not psychologists. However, the fact is, nostalgia sells, and business researchers are very interested in understanding exactly what nostalgia is, who is most prone to react to it, and how it contributes to business success. Toy companies like Hasbro have realized that adults buy toys for kids to enjoy. Thus, the toy shelves are filled with throwback versions of G.I. Joe. The question is, how can organizations better integrate nostalgia into their business plans? Researchers are working on numerous issues related to nostalgia. How can nostalgia be measured? What emotion is nostalgia associated with? Can market segments be defined based on the type and amount of nostalgia experience? What happens to consumers when they experience nostalgia? What makes a nostalgic consumer different from one who does not experience nostalgia? What are the positive outcomes for the business when consumer nostalgia increases? Multivariate procedures can help address this question as they consider the effects of multiple variables.
What is multivariate data analysis? What is a variate?
Mathematically, the variate is a function of the measured variables involved in an analysis. In this equation, Vk is the kth variate. Every analysis could involve multiple set of variables, each represented by a variate. x1 to xm represent the measured variables. Here is a simple illustration. Recall that constructs are distinguished from variables by the fact that multiple variables are needed to measure a construct. Let's assume we measured nostalgia with 5 questions on our survey. With these 5 variables, a variate of the following form could be created. Vk equals L1 x1 plus L2 x2 plus L3 x3 plus L4 x4 plus L5 x5. Vk represents the score for nostalgia. X1 to X5 represent the observed scores of the 5 scale items from the survey questions that are expected to indicate nostalgia. And L1 to L5 are parameter estimates, much like regression weights, that suggest how highly related each variable is to the overall nostalgia score. This presents a very basic classification of multivariate data analysis procedures. 2 basic groups of multivariate techniques are dependence methods and interdependence methods. Which multivariate approach is appropriate? Dependence techniques are multivariate statistical techniques that explain or predict one or more dependent variables. When hypotheses involve distinction between independent and dependent variables, dependence techniques are needed. For instance, when we hypothesize that nostalgia is related positively to purchase intentions, nostalgia takes on the character of an independent variable and purchase intentions take on the character of a dependent variable. Predicting the dependent variable sales on the basis of numerous independent variable is a problem frequently investigated with dependence technique. Multiple regression analysis, multiple discriminant analysis, multivariate analysis of variance, and structural equations modeling are all dependence methods. Interdependence techniques is a multivariate statistical techniques that give meaning to set of variables or seek to group things together. No distinction is made between dependent and independent variables. When researchers examine questions that do not distinguish between independent and dependent variables, interdependence techniques are used. No one variable or variable subset is to be predicted from or explained by the others. The most common interdependence methods are factor analysis, cluster analysis, and multidimensional scaling. A manager might utilize these techniques to determine which employee motivation items tend to group together, to identify profitable customer market segments, or to provide a perceptual map of cities being considered for a new plan. In other forms of data analysis, the nature of the measurement scales will determine which multivariate technique is appropriate for the data. These diagrams shows that selection of multivariate technique requires consideration of the types of measures used for both independent and dependent sets of variables. These refer to nominal and ordinal scales as non-metric and interval and ratio scales as metric. Regression analysis is another technique for measuring the linear association between a dependent and an independent variable. Although simple regression and correlation are mathematically equivalent, in most respects, regression is a dependence technique where correlation is an independence technique. A dependence technique makes a distinction between dependent and independent variables. An interdependence technique does not make this distinction and simply is concerned with how variables related to one another. Thus, with simple regression, a dependent or criterion variable y is linked to an independent or predictor variable x. Regression analysis attempts to predict the value of a continuous interval-scaled dependent variable from specific values of the independent variable. Here, simple regression investigates a straight line relationship of the type. On the other hand, multiple regression analysis is an analysis of association in which the effects of two or more independent variables on a single interval-scale dependent variable are investigated simultaneously. It is an extension of simple regression analysis, allowing a metric-dependent variable to be predicted by multiple independent variables. To further understand this topic, let's take a look at this example.
So when we're looking to predict the value of a variable, oftentimes we can get better predictions if we use more than one other variable to make that prediction, and that leads us to multiple regression. Now, I am going to assume you have some familiarity and some comfort with simple linear regression, which we covered in the previous series. So if you're still a bit shaky on just simple linear regression, I would go back, review that, and then come back to this series. So without further ado, let's go ahead and get to learning. So as always, let's start out with a problem and a data set that we're going to use for the next several videos. And this is called the Regional Delivery Service. So let's assume that you are a small business owner for Regional Delivery Service Incorporated, or RDS for short, who offers same-day delivery for letters, packages, and other small cargo. You are able to use Google Maps to group individual deliveries into one trip to reduce time and fuel costs, just like UPS would or FedEx or the Postal Service does. Therefore, some trips will have more than one delivery. Now, as the owner, you would like to be able to estimate how long a delivery will take based on two factors. One, the total distance of the trip in miles, and two, the number of deliveries that must be made during that trip. So, we're looking to estimate how long a delivery trip will take based on the distance and the number of deliveries during that trip. So, two factors. So to conduct your analysis, you take a random sample of 10 past trips and record 3 pieces of information for each trip. 1, the total miles traveled. 2, the number of deliveries during that trip. And 3, the total travel time in hours, which is what we're trying to predict. So you make a table that looks like this. So we have miles traveled, num deliveries, which is the number of deliveries, and then travel time in hours along the top. We have labeled them x1, x2, and y. Now x1 and x2 are special types of variables we'll discuss here in a minute, and y is a distinct variable we'll talk about here in a minute. So we can see the first trip, we traveled 89 miles, we had 4 deliveries on that trip, and the total time was 7 hours. The second trip was 66 miles, we only had 1 delivery, and the travel time was 5.4 hours. So here are our 10 trips. Now remember that in this case, you would like to be able to predict the total travel time. So that's the right column, sort of in the orange-brown color there. Using both the miles traveled, which is x1, the first column, and the number of deliveries, which is the second column, x2, of each trip. So the question is, in what way does travel time depend on the first 2 measures, miles traveled and number of deliveries? So travel time is the dependent variable, and miles traveled and number of deliveries are independent variables. Now one note here, some prefer predictor variables and response variable instead of independent and dependent variables respectively. Since most stats textbooks use independent variable and dependent variable, I am going to stick to that. But I do subscribe to the case of predictor variables and response variable. Just keep in mind that depending on the textbook you're using and your professor and things, you may hear both or one or the other. So what about multiple regression? So multiple regression is just an extension of simple linear regression, again, which we talked about in the last series. So remember, in simple linear regression, we have a one-to-one relationship. So we have a dependent variable, and we're going to utilize an independent variable to explain the variation in that dependent variable or make predictions about that dependent variable. Now, in multiple regression, we have a many-to-one relationship. So we still have one dependent variable, but we can have 2 or more. So in this case, we have 4 on the screen, but we could have more than that, or just 2 or 3 or whatever independent variables that are all being utilized to explain the variation or predict the value of the dependent variable. So we go from a one-to-one relationship, one independent to one dependent, to 2 or more independent variables and 1 dependent variable. Now, having more independent variables complicates things a bit, so we have to have some new things to consider. The first is that adding more independent variables to a multiple regression procedure does not mean or necessarily mean the regression will be better or offer better predictions. In fact, doing so can actually make things worse. This is called overfitting. So let's say we conduct a multiple regression procedure and our model explains 65% of the variation in the dependent variable. Well, for some reason, we don't like that. We think, well, we can do better than that. So we start adding in more independent variables. Well, adding more independent variables will explain more of the variation in the dependent variable, but it can do so under false pretenses. So adding more variables will always explain more variation, but it can open up a whole Pandora's box of other problems that we definitely want to avoid. So we'll talk about that more as we go, but I just want to float it out there that dumping more variables into a multiple regression procedure is not the way to go. The idea is to pick the best variables for the model. We'll talk about how to do that in future videos. The other concept is that the addition of more independent variables, see a pattern here, creates more relationships among them. So not only are the independent variables potentially related to the dependent variable, they are also potentially related to each other. Now when this happens, it is called multi-collinearity. Now it's a mouthful of a word to say, and I stumble over it sometimes, but hopefully we'll get better at it as we go. So it's called multi-collinearity when the independent variables are correlated with each other. So the ideal, the perfect world, is for all of the independent variables to be correlated with the dependent variable, but not with each other. And again, we'll talk about overfitting more as we go. We'll talk about multi-collinearity more as we go forward. And just keep in mind that the ideal is for the independent variables to be correlated with the dependent variable, but not with each other. Now, because of multi-collinearity and overfitting, there is a fair amount of prep work to do before conducting multiple regression analysis if one is to do it properly. And in a future video, we will walk through all those things step by step so that you form the best model you can. So things like correlations, scatter plots, and some simple regressions between the independent variable, each one of them, and the dependent variable, just to see how they're related. So to do multiple regression properly, really running the multiple regression is the very last step. There's a lot of prep work to do before doing that, and again, we'll talk about it as we go. So as we talked about before, adding more independent variables creates more relationships among all the variables. So we have this many-to-one relationship. Now in our problem, we have a dependent variable that is the travel time. We are trying to predict the travel time of these trips. Now we are utilizing two independent variables that we selected. We have miles traveled, that's our x1, and then we had the number of deliveries, or num deliveries, which is our x2. Now we'd like to utilize those two independent variables to make predictions about the dependent variable. Now by setting it up this way, we also create a third relationship, and that is the relationship between the two independent variables themselves. So we don't have just two relationships, independent to dependent. We now have a relationship between the independents. And having that relationship sets up the potential multi-collinearity risk. So we're going to have to see when we do this problem whether or not these two independent variables are correlated with each other. And the easy way to think about this is that if these two independent variables are related to each other, we're really not sure which one is explaining the variation in the dependent variable. So if I put sea salt and table salt in my dinner, all I know is that it tastes salty. But I can't tell the difference necessarily between the two because they're both salt. They have the same relationship to my now salty dinner. So we want to have a distinction between the independent variables so they explain something different. They have a different relationship to the dependent variable over here on the right. So we will walk through that analysis as we go forward. Now let's look at this situation. So here we have one dependent variable and four independent variables. So we know we have the full relationships with each independent variable and the dependent variable. So right there, we already have four variable relationships. But we're not done. We have to account for all the relationships between the independent variables. And that's 6 more. So now, with 4 independent variables and 1 dependent variable, we have 10 relationships we have to consider. Now you can see, as each independent variable is added, these relationships become very numerous. So part of the art of multiple regression is deciding which independent variables make the cut and which do not. And we'll talk about that as we go, of course. So So the bottom line is that some independent variables, or sets of independent variables, are better at predicting the dependent variable than others, and some independent variables contribute nothing. So we'll have to decide which independent variables to include in our model and which ones to exclude. So again, the ideal is for all of the independent variables to be correlated with the dependent variable, so the orange lines, but not with each other, so the colored dotted lines here. So this slide is not something you have to really commit to memory, but I just want to show you sort of where the multiple regression model comes from. So we have our multiple regression model, which is y equals beta sub 0 plus beta 1 x1 plus beta 2 x2 plus etc, etc, etc. P just means the number of variables we have plus epsilon. Now over here on the left, what we have are the sum of linear parameters. So we have beta sub 0, which is our intercept, and then we have beta 1 x1, which is one variable and its weight. Then we have x2 beta 2, which is another variable and its weight, etc, etc. So it's just the sum of some linear parameters. Then over here on the right, we have our error term. So we've seen this before in simple linear regression. So we have an intercept plus a set of linear parameters plus an error term. Now for the multiple regression equation, we have the expected value of y equals everything we see up at the top, but there is no error term. Well, why is that? That's because in the multiple regression equation, the error term is assumed to be 0. So 0 is 0, and therefore it's not on the end of that equation. The one we're going to be familiar with is the estimated multiple regression equation. So again, when we're using sample data, it's never going to be perfect. We're estimating, so we have to use the estimated multiple regression equation. So y hat is the predicted value of y equals b sub 0 plus b1 x1 plus b2 x2, etc. As you can see, it follows the same form as the multiple regression equation above it, and everything that you see at the bottom is just an estimate of what is above it. So b0, b1, b2 are all the estimates of beta 0, beta 1, beta 2, etc. And then y hat is the predicted value of the dependent variable. So again, this is not something you need to really commit to memory, but I just want you to see the pattern of how these multiple regression equations are going to look, and we'll talk about in the next slide sort of what they mean. So let's go ahead and look at an example. So this is a multiple regression equation you may generate based on some analysis you conduct. So we have y hat equals 6.211 plus 0.014x1 plus 0.383x2 minus 0.607x3. So this is a standard form of a multiple regression equation you may generate. Now if we look at our estimated multiple regression equation, so we have y hat equals b0 plus b1x1 plus b2x2, etc. If you look at that and compare it to the equation at the top, you can see that they're very similar. We just have some stand-in numbers that we have to interpret. So we have our variables, so x1, x2, and x3 are our variables, and we can see that they're in place there at the top and of course in the equation at the bottom. Then we have some coefficients and an intercept. So 6.211 is our intercept, which corresponds with b sub 0 in the equation below. Then we have 0.014 there in the blue, that corresponds to the first coefficient on the bottom, etc, etc. So we follow the same basic form, intercept plus some coefficients paired with a variable. So coefficient with a first variable, a coefficient with the second variable, and in this case a coefficient with the third variable. And again, these are all estimates of the multiple regression model. So how do we interpret the coefficients in multiple regression? They're interpreted a bit differently than they are in simple linear regression. Let's take this example. So we have y hat equals 27 plus 9x1 plus 12x2. Now, everything we see here is in thousands of dollars. So x1, that's our first variable, stands for capital investment in the thousands of dollars. So x2 stands for the marketing expenditures in thousands of dollars, that's there in the blue. And of course y hat is going to be our predicted sales in thousands of dollars. So everything is in thousands of dollars. We have to keep that in mind as we go about interpreting it. So in multiple regression, each coefficient, so we have our 9 and our 12 up there, is interpreted as the estimated change in y corresponding to a 1-unit change in a variable when all other variables are held constant. So what does that mean in this problem? So in this example, $9,000 is an estimate of the expected increase in sales, which is y, corresponding to a $1,000 increase in capital investment, which is our x1 up there. So remember, everything's in thousands of dollars, so I'm just making sure it's actually in dollars here at the bottom. So $9,000 is an estimate of the expected increase in sales corresponding to a $1,000 increase in capital investment, which is x1. Well, why is that? Look at the coefficient with our x1 variable up there. It is 9. So if we increase x1, where x1 is the number 1, we have 9 times 1, so that's 9 times $1,000. So that's $9,000. Assuming we hold the x2 over here on the right constant. And that's how we interpret the coefficients in multiple regression. We could flip that and say, well, $12,000 is an estimate of the expected increase in sales y, corresponding to a $1,000 increase in marketing expenditures when capital investment is held constant. So a 1-unit increase when everything else, all the other variables, are held constant. And again, we'll be doing this more in future videos, so we'll get some practice at it, but that's the basic idea how we interpret coefficients in our multiple regression equation. So let's go ahead and do a quick review, and then we'll be done with this first video. So multiple regression is an extension of simple linear regression. 2 or more independent variables are used to predict or explain the variance in one dependent variable. 2 problems may arise, however: overfitting and multicollinearity. So overfitting is caused by adding too many independent variables. They account for more variance, but really add nothing more to the model. Then multicollinearity happens when some or all of the independent variables are correlated with each other, and it becomes hard to tell which is actually predicting or explaining the variance in the dependent variable because they're so similar. In the multiple regression, each coefficient is interpreted as the estimated change in y, the dependent variable, corresponding to a 1-unit change in a variable when all other variables are held constant. And again, we'll practice that more as we go.